All right. Um, this is escape velocity. Okay. All we gotta do so the total mechanical energy. Or sorry, I should probably read the problem first. Consider small mass m and large mass big M subject only to their mutual gravitational attraction. Assume that little m is much smaller than big M and the objects are a distance r apart, and that the small mass m moves with speed v. To get the total mechanical energy of the small mass m, well, I know that total mechanical energy is equal to the sum of kinetic plus potential, and if they're only subject to the gravitational attraction, then the kinetic energy is going to be the same, 1/2 mv squared as always, but the potential energy is going to be where it differs, and that's going to be negative g little m big M over r. Okay, um, and so that's going to be the total mechanical energy of the small mass little m. If you ever see somebody or you ever hear the phrase in like physics about like escaping one of the masses, this means so like to say the small mass escapes the larger mass, that means that the small mass reaches infinity, okay, where the potential is equal to 0 before it can reverse direction and return to big M. Okay, so that means that basically it reaches infinity before it can. So if it reaches infinity, then it essentially escapes the larger mass. It doesn't ever return back to M. It's escaped the gravitation or the pull of big M. Okay. Um, this says what must the small mass's total energy be if it's to escape the larger mass. This really should say what is the minimum condition for it to do that. And the minimum condition is that the total energy would be equal to 0. Okay? And the reason for that is because if I look at kinetic initial plus potential initial equals kinetic final plus potential final, okay? Well, the whole left side term cannot be negative. Okay? The whole left term cannot be negative because that's the total amount of energy that you start out with. You have to have some amount, okay? It can be 0, but it cannot be negative, right? You cannot have negative energy, okay? Well, on the right side, this the kinetic energy can only ever be positive or 0. So this has to be minimum of 0, cannot go lower than that, cannot go negative. And then the final gravitational potential energy cannot make the right side negative. So this it can be, so the final gravitational potential energy will be a negative term. It'll subtract from the kinetic, but it cannot make right side negative. Okay. Um, and so that's kind of showing why total energy should be equal to 0. That's like the minimum condition. It can have some energy and still escape, but really this is the minimum condition. This is all we need to really worry about. It is possible, I believe, for masses to be able to escape and not have 0 total energy, but this is really for this class all you need to know regarding that. So I would not worry too much about anything else. I would just say that if a problem asks you that, hey, this mass escapes this mass, then you would need to say that the total energy would need to be 0. Okay. Um, okay. And then expression for the escape velocity. This is basically the velocity that makes the total energy equal 0. Okay. So what I can do is I can do 0 equals 1/2 mv. I'm going to call this v escape, ESC, okay, squared, minus g little m big M over r, okay. Use capital R for consistency because it says that they're a distance big R apart from each other, okay. Um, okay, and then I can find out from here that this is just 1/2 mv escape squared equals g little m big M over r. Okay. Okay, because those two are going to have to be equal to each other to get it to be equal to 0, right? And then what you can do is that I'm going to take I can take my little m's and cancel them out. Okay. And all I got to do now is just multiply by 2 and root both sides. So I should see that v escape squared is equal to 2g big M over r. And then if I root both sides, I get v escape is equal to root 2gm over r. Okay, and that is it. That's it for escape velocity. That's the equation, right? That's how fast that the small object would need to go to escape the larger object. Okay. Okay, that's escape velocity. That's all you got to know for escape velocity. Okay.